In the first and second part of this video lecture, we saw definition and examples of measures. We proved some of its main properties, and now in this third part of this video lecture, we'll talk about the Lebesgue measure and about probability measures. Recall, a measure is a non-negative function that assigns value 0 to the empty set and assigns the sum of measures of the sets to the union of those sets if they are disjoint and if they are all members of the sigma algebra. The basic properties of measures were countable subadditivity, continuity from below, and continuity from above, which has this important assumption here. In the lecture notes you can see a counterexample for the case when this is violated. We now describe and introduce very briefly the Lebesgue measure, postponing the proofs to subsequent lectures, which will happen next week. So here's the theorem. The Lebesgue measure, it says there exists a unique measure. We call that measure M. Where's that measure? That measure is on the sample space set of real numbers, and as the sigma algebra, it is the Borel sets. So there is a unique measure on this measurable space here that assigns B minus A to any interval starting at A and ending at B for two numbers, finite numbers A and B with B larger than A. This measure M, this unique measure M, satisfying this equation for every A and B, this measure M, it is called the Lebesgue measure on the real line. Now in particular, the measure of a set which has only one point in it, so that's a closed interval that starts and ends at the same point, it is 0. And because measures are countably additive or sigma additive, then any countable set also has measure 0. In particular, the set of rational numbers, it does have measure 0. So if we would assign a length to the set of rational numbers, it would have been 0, even though the set of rational numbers, it is present everywhere. Okay, it's present everywhere in the sense that it will intersect every interval, however tiny it is. Even though it intersects every interval, and in this sense we can say it's present everywhere, its length is actually 0. Another very important measure is when we restrict the Lebesgue measure to an interval. So we restrict the Lebesgue measure to an interval by assigning to every Borel set of the real line just the measure of the part of that set that overlaps with this interval AB. So we can consider this restriction. Mu is the restriction of the measure Lebesgue measure M to the interval AB. We now talk about probability measures. So what is a probability measure? A probability measure is nothing but a measure that assigns total mass 1 to the entire probability, to the entire sample space. So a probability measure assigns value 1 to the sample space, so the sample space cannot be empty, and this is called a probability measure. So it satisfies if a function defined on a sigma algebra F, it satisfies all the axioms of being a measure plus assigning value 1 to the entire sample space, then it is called a probability measure. And to this triple, omega, F, and this measure mu, we call it a probability space. Moreover, we don't really want to call it mu. If we know beforehand that a measure is a probability, we'll usually call it P, or boldface P, or blackboard boldface P. In this module, we'll be almost all the time using this one, the blackboard boldface P, instead of mu or nu or any other Greek letter to denote a measure, when we know beforehand that that measure is a probability measure and when that property is relevant to us. Here is the simplest example of a probability measure. It is the case of equiprobable outcomes. So we have a natural number, non-zero number n, and omega b is, let omega be a sample space that has exactly n elements in it. We take it as the sigma algebra the set of all subsets of omega, and for each element of omega we consider the Dirac mass function delta subscript omega that assigns mass 1 to sets that contain omega and 0 to sets that do not contain omega. So this here puts mass 1 on this point omega and mass 0 elsewhere. When we sum over all elementary points lowercase omega, then we get the counting measure on this sample space omega. And if we divide this measure by n, then we get a probability measure. Okay? And this probability space here, it is the model of equiprobable outcomes. Now again, when the sample space is still finite, so the sample space has n elements, omega 1 up to omega n, and we define E to be the class of sets that consists only of the singletons. It has A1 up to AN, where each of these sets is just a set with one element from the sample space. Then if we define the probability of this set AI, which is the same as saying the probability of the set that only contains one element of omega, which we call lowercase omega I, we define this to be some number pi greater than or equal to 0, some non-negative number pi, and such that when we sum over I all these pi's, we get 1. So these pi's are really a function that maps to each index I. They give a probability. Okay. Then we can extend this definition of p that was defined so far only for sets in this class. We can define it to any subset of omega just by imposing the requirement that it be finitely additive. And then we can check that p defined this way will indeed define a probability measure on omega with the sigma algebra parts of omega.